First thing I would do in these situations is maybe draw yourself a little diagram so you can picture all the variables. So I'm going to draw out, here we are, the building. And the building is 30 meters high. Okay, he stands up here. And then 5 meters from the base of the building is the pool. And so in this example, he's going to jump off horizontally. He's going to have a Vx. He's going to have an x component to his velocity. Okay, and that's going to cause him to move that way while he's falling. And hopefully while he's falling, he travels far enough in the x direction that he lands in the water. Okay, so the question is how hard, or with what velocity does it need to push off in order to be able to be over the water by the time he reaches the ground? So that's what we want to figure out. Now, in these problems, you want to think x and y separately. So we want to look at x direction variables, and we want to look at y direction variables. Okay? So remember our three kinematics equations, they deal with accelerations, right? All the acceleration is going to happen in the y direction. So these three equations are going to be used for your y direction. So we're going to list the 5 variables here, the y variables. VIY, Fy, delta dy, g, and delta t. Now in the x direction, there's no acceleration, right? There's no forces pushing him or pulling him in the x direction. So because of that, we don't need these equations. Okay? If we were to make acceleration 0 in this equation, then we have Vf equals Vi. That's not very helpful. If we're to make acceleration 0 here, we have Vf equals Vi. Again, not very useful. If we make acceleration 0 here, we're left with delta d equals V delta t. And that is basically our equation, remember, for average velocity. So in the x direction, we only need to worry about one equation. And that's going to be delta dx equals Vx delta t. And you'll notice here I just put x. I don't have a Vix or a Vfx, because since there's no acceleration, the velocity doesn't change. So it's just Vx. Okay, so in the x direction, we have 3 variables to worry about. Vx, delta dx, and delta t. Okay. Now, in our problem, what are some of the variables that are given in the description of the problem? Alex?
The 5 meters for distance.
Which distance?
For distance x.
X, right. So we know 5 meters is the distance we want to see him go in the x direction. What else was given? Alex?
The distance in the y, which is 30.
30. Right. Remember, this is a displacement, so he's ending up below where he started, so it's actually going to make that negative. And there's one more we can kind of infer from the problem. He's coming off horizontally. This one, right? So this is 0. Okay. Now, ultimately, we want to know what does his x velocity need to be. So that's Vx. We want to know what is this Vx going to be. To get that, we're going to need some time information. Time is the one variable that's going to be the same for x and y. There's not an x time and a y time. There's just time. So can we get time from what's given over here with the y variables? And we can. We can use our second equation to get time. So delta dy, VIY delta t, 1/2 g delta t squared. Now VIY is 0, so that's canceled. So then we have negative 30, 1/2 negative 9.8 times squared. And if you solve for time, you find that he falls for 2.5 seconds. And that's how long he's in the air. So in 2.5 seconds, we need him to get right to here, to the water's edge. So if we make this 2.5 seconds, and then use our x equation, we've got 5 equals Vx times 2.5. And so he needs to jump off horizontally with a velocity of 2 meters per second. And then that way he'll be over the water